너무한 거 아니야? 항생제, 베타라탄. 그걸 뭐 주고 쓰는가? 이게 베타라는 걸 뭐 주고 쓰는가? 빨리 와. 이 폰트 쓰는 거 있잖아. 이태릭체도 있고 그릭체도 있고. 이태릭체는 이태리 전부 다 이태릭체 쓸 줄 알았는데 이태릭체 안 쓰더라고. 한 50정도 쓰는데 그리스로 하면 그릭체를 쓸까? 다 우리 알파벳 쓰는 거 아니야? 그리스 가니까 진짜 이런 거 쓰더라고. 알파벳 그리고 알파벳을 다는 몰라도 알파, 베타, 감마는 영어 알파벳을 뭐에 해당하지? C인가? 순서는 C인데 C 아니야. G야. 그러니까 감마 순서가 바뀌었다는 얘기지. 그리고 델타, 입실론, E 이렇게 꽂는 거 선생님 거. 그 정도까지는 알면 좋겠고, 그지? 파이 이런 거는 쓴 거 있으니까 알 테고, 지금 안 해도 수학에서 쓰니까 알 테고, 베타락감 정도는 필터로 봤을 거 아니야? 왜냐면 랩 사이언티스트 아니면 엔지니어잖아? 아니면 그것도 될 거고. 락탐은 사이클릭 아마이드가 락탐이고 락토는 사이클릭 테스트가 락토이던지 워킹이 되면 이게 알파, 베타 하나 더 있으니까 감마 락톰이라고 부른다든지 발음을 위치는 1번이지만 알파, 베타로 따질 때는 발음을 강타하지 않고 모르게 되면부터 알파, 베타 이렇게 부르는 거지. 연락해서 나온다. 근데 도망 이거 모르는 거 아니야? 너 여기 안 떴어? 넣어줬어? 끊겼어? 베타 아미노스도 많네. This is the structure of an amino acid. Alpha amino acid. If it's a 2-carbon, then beta amino acid. The basic amino acids in our body, the protein structure is based on alpha amino acid. 대충의 값은 알고 있으면 되게 도움이 될 pKa밖에 안 되었어. 카르보시 애시드 4에서 왔다 갔다. 어떤 건 3도 되고 5도 되겠지만 대충 사실도 알고 있으면 되겠군요. 오케이. 위계 시드라 그랬고 7을 중심으로 해서 4, 5, 10이니까 다 30 떨어져 있고 1000개 중에 한 개씩. 카르보게 시드 같으면 1000개 중에 한 개가 애시드 폼으로 있고 나머지는 떨어진 카르복실레이트 폼으로 있는 거고 펜은 반대로 1000개 중에 한 개가 O-로 떨어져 나오고 나머지 999개는 페놀 폼 그대로 OH 폼으로 있는 거고. 오케이. 정도면 위계시드 윗베이스. C를 중심으로 전배 이쪽으로 이쪽으로 둘 다 C들어가 가지고 100% 방면이니까. 자, 오늘 PK 얘기를 많이 하는 건 수업에 그 얘기를 하겠다는 얘기지. 오케이, 14, 16, 뭐 대충 그 정도, 물도 비슷하고 알코올에서 떼내는 거는 상당히 어렵다. 잘 안 떨어진다. 대부분은 다 붙어 있다. 7하고 거리를 생각하면 10 to the 마이너스 9승쯤 되네. 10 to the 마이너스 9승이면 15배다, 그지? 15배 중 한 개가 프로톤을 내는 겁니다. 거의 다 뉴트럴 폼이에요. 물도 그렇고 알코올도 대충 거의 한 개. 저 정도 되면 적정한 것도 어려울 거야. 그래서 14는 16이 더 큰 차이 없어. 대충 그 정도 영역이다. 메탄올에서 프로톤 된 거는 메탄사이드. 또 리더튼트 악시던트 이거 계속 얘기해도 틀린 사람 있네. Reductant accident and acid base, the base difference is reductant accident. Reductant base give electron. Reductant give permanently. Base 그냥 주는 척 pretend to give. 그렇지만 나중에 돌을 찾아가. 줄급처럼 가까이 가서 흔들어 놓지만 마음은 흔들어 놓고 샥 떠나. 그래서 베이스는 캐리리스트고. Acid accident. 일렉트론을 뺏어가는 거. 그런데 애시드는 살짝 끌어당겨가는 척하지만 결국은 도로 주고 떠나. 그래서 애시드도 캐리리스트야. 악시던트는 전자 확 뺏어서 영원히 달아나. 오케이. 여기에 있는 얘들은 프로톤이 붙었다 떨어졌다 하지만 영원히 일렉트론을 가져가거나 주거나 하지는 않아. 얘는 OH 상태로 있을 때는 weak 애시드였는데 무작위 위계시되었기 때문에 그거의 컨주게이트 베이스는 상당히 스트롱한 베이스예요. 다시 말해서 프로톤을 받아서 OH로 돌아가려고 하는 성향이 크다 이런 겁니다. 프로톤만 가져가지 전자를 가져간 건 아니야. 말이 잘못됐네. 프로톤만 가져가지 전자를 완전히 프로톤한테 준 건 아니야. 프로톤이 떠날 때 그 전자를 도로 주고 가. 그지? 그게 베이스예요. 그래서 쟤는 베이스. weak acid의 conjugate base는 strong base. strong acid의 conjugate base는 weak acid. 맞게 말했나? strong acid의 conjugate base는 weak base. CL 마이너스 같은 거. 오케이? 알킬리즘하고 가장 비슷한 게 뭐지? 알킬리즘하고 거의 비슷하다고 같다고 생각하시는 거? 다시 그렇지. 다시 유기구리. 유기구리는 조금 더 말랑말랑해진 거고 그보다 좀 더 가까운 건 그리냐리 레이전트지. MGBR이면 리튬 알킬리즘하고 거의 비슷하다고 볼 수 있고 유기구리점 가면 좀 더 말랑말랑한 거로 바뀐 거야. 우리하고 침팬지 사이냐? 아니면 우리하고 조금 더 먼 오랑우탄 사이냐? 뭐 이런 얘기야. 그러니까 구리점 가면 누가 프로퍼티 비슷한데 R-, 카본 마이너스 뉴클레오파일일 수도 있고 일렉트로파일은 아니지. 일렉트론이 넘치니까 뉴클레오파일일 수도 있지만 동시에 베이스일 수도 있다. 모든 뉴클레오파일은 혹은 모든 베이스는 앞에서 말한 에석사이드도 베이스라고 우리가 지칭했지만 뉴클레오파일일 수도 있지. 공격해서 일렉트로필릭한 포지션을 때려서 반대를 만들 수도 있으니까 베이스하고 뉴클로파일은 역할에 따라서 양쪽 다 할 수 있어. 뉴클로파일의 파트너는 일렉트론이 부족한 카본이야. 그지? 베이스의 파트너는 베이스는 누구한테 일렉트론을 줘? 누구한테 줄까? 여러분 잘 아는데 누구한테 줄까? 프로톤한테 주는 거지. 그 일렉트론이 프로톤한테 인치로 완전히 준 거 아니라 그랬지. 프로톤한테 동요되면 베이스, 카본한테 가서 그 공유를 하면 뉴클로파일. 아킬 리튬이 일반적으로는 우리가 앞에서 배웠던 거는 뉴클로파일로 작용하는 걸 주로 배웠을 텐데 그린다드 리전도 비슷하게 오늘 이 챕터에서 배울 역할은 아킬 리튬이 베이스로 작용하는 걸 배울 거기 때문에 그거 한번 많이 배워주고 싶었어요. pK 한번 따져볼까? 아모늄이나 아모니아나 아민의 pK가 얼마였지? 제가 생각했잖아. 요거하고 비교하면서 누가 더 강한 베이스일까? 비교하면서 아민의 pK는 피리딘의 pK는 뭐 생각나는 거 뭔지 아무거나. 피리딘 5 정도, 아민 10 정도. 이건 애시드티가 반대니까 아민이 얘가 더 윅 베이스고 스트롱 애시드니까 얘가 더 스트롱 베이스고. 오케이? 아까 알코사이드는 알코올의 pK가 얼마라고 그랬어? 16 정도 된다고 그랬네. 5, 10, 그거만 해도 10만 배인데 다시 16이니까 그게 10만 배. 그래서 OH-나 알코올사이드나 이런 애가 아민보다 10만 배 더 스트롱한 베이스. 피리딘은 그보다 10만 배 더 약한 베이스. 그렇지? 피리딘은 굉장히 약한 베이스니까 굉장히 리액티브하고 반응하면 여전히 베이스로 사용할 수 있다. 아실 할라이드 같은 거. 가장 리액티브한 아실 리에이전트. 거기는 피리딘만 써도 반응이 간다. 그보다 좀 더 반응성이 떨어지는 것들은 좀 더 강한 베이스를 써야 되는데 순서를 생각하면 아민 베이스가 10만 배 정도 강하고 그 다음에 소듐 하이드록사이드 혹은 소듐 에석사이드 이런 걸 쓰면 다시 10만 배 정도 더 강하다. 대충의 순서로 베이시스의 순서. 카르복실레이트 pK가 4 정도 된다고 그랬고 HCl 같은 거는 뭐 마이너스 값이잖아. 그러니까 그게 0 가까이 간다고 생각하면 다시 거기도 10만 배 정도 더 강한 애시드로 같대. 약한 애시드는 비교적 약한 애시드는 카르복 애시드 반응했을 정도 되거든. 그 정도를 정리하면 대충 오게닉 케미스트리에서 나오는 pK는 대충 머릿속에 다 들어갔다고 볼 수 있어. 그래서 지금 답을 다 말해버렸네. 아깝다 말해주는 거 틀리진 않겠지. 10이라고 그랬잖아 금방 그랬잖아. 여기까지 들으면 수업하네. 사실 두 명씩은 도대체 아이 참. 자, 이것 때문에 헷갈렸을까? 내가 피리딘의 pK가 얼마냐 하고 암모니아의 pK가 얼마냐 이렇게 물었을 때 이때까지는 pK 값은 그게 프로토네이션 되어 있는 형태에서 프로톤을 주는 효과인 거야. 그걸 pK를 못하는 거야. 그러니까 따져보면 암민에서 암모니아에서 NH3에서 NH2로 바뀌는 것도 프로톤을 낼 수가 있는 거잖아. 지금 그거 얘기하는 거 아니야. 프로톤이 붙어 있는 상태에서 프로톤을 내놓는 정도를 따지는 pK를 지금 보고 있는 거야. 그래서 이름을 암모늄이라고 불렀고 피리디늄이라고 불렀어. 그 두 개는 다른 현상이에요. 중간에 뉴트럴한 NH3가 있는데 NH4 플러스에서 1로 가는 거. 지금 그거 얘기하는 건데 우리가 베이스로 작용한다고 하는 거는 뉴트럴한 상태에 프로톤이 가서 붙는 거잖아. 그래서 베이시스트가 있다고 얘기하는 거고, 그런데 NH3에서 NH2로 가는 거는 그건 다른 반응이야. 그거 얘기하고 있는 거 아니야. 지금 얘기하는 거. 오케이? 베이시스트를 얘기할 때는 프로톤이 붙는 거니까 붙은 상태에서 떨어지는 pK를 얘기하는 거야. 붙는 거를 pKb로 표현해서 따질 수도 있지만 같은 유닛으로 그거는 뒤집어서 따지면 되기 때문에 같은 유닛으로 볼 때 지금 얘기하는 pK는 프로톤이 붙었다가 떨어지는 걸 보고 있는 거야. 다시 한번 정리해볼까? 카르복실레이트 COOH 상태에서 H를 내놓는 거, 그거 따지고 있는 거야. 4정도. 피놀 OH에서 O 프로톤 내놓고 O 마이너스 되는 거, 그 과정을 따지고 있는 거고, 그거 10정도. 아민 20이라고 얘기할 때는 이 아민의 10은 아민의 프로토네이션 돼 있던 게 플러스 차지로 갖고 있던 게 프로톤 내놓는 거, 그게 10정도라는 얘기야. 오케이? 그러면 페놀하고 아민하고 누가 20이고 누가 베이스인가요? 폼이 둘다 값은 10이지만 따져보면 그 10일 때 pH 7일 때 상태가 어떻게 되냐는 걸 따져보면 천개 중에 한 개가 뭐 이런 얘기잖아. 3개가 건너뛰어 있으니까 페놀은 천개 중에 한 개가 프로톤을 내놓는 상태, O- 상태. 아민은 천개 중에 한 개가 뉴트럴한 상태. 999개는 프로톤이 붙은 상태. 그 말이에요. 그러니까 걔는 베이스고 페놀은 위계식. 오케이? 프로톤을 가져갔으니까 베이스잖아. pK 값이 둘 다 10이지만 따지고 있는 게 다른 걸 얘기하고 있는 거야. 그래서 아모니아나 아민은 베이스고 1000개 중에 한 개 남겨놓고 다 프로토네이션 됐습니다. 피놀은 1000개 중에 한 개만 프로톤을 내놨으니까 위계식으로. 오케이? 피리디는 pH 7에서 100개 중에 한 개만 프로토네이션이 되어 있고 나머지 99개는 뉴트럴 폼이야. 그래서 위크 베이스. 오케이? 자, 그 정도 하면 지금 가장 많이 쓰는 것들의 pK 값은 대충 정리한 거야. 물이나 알코올은 pK 값이 14, 15, 16. 오케이? 대부분은 뉴트럴 하라는 얘기고 어쩌다 한 개씩 프로토네이션, 프로톤을 어쩌다 한 개씩 프로토네이션이 된다. 오케이. 오케이. 유형결 Chapter 22. 다음 주 한 주만 더 하면 벌써 또 다음 시험이네. 빨리 갔다 오지. 카르보닐 계열의 거 공부하고 있는 거 중간 거 지났고 이제 카르보닐의 이제 남은 두 개 중에 한 챕터를 공부하게 되는데 오늘 공부할 자리는 이거 알파라고 했지. 카르보닐의 알파 포지션에 대한 시험 반응을 보게 되겠습니다. 자, 지금까지 했던 걸 생각해 보면 we had studied about the carbonyl group so far, and carbonyl's property was this electronegative electron withdrawing, and this is delta minus here, this delta plus here. And first reaction we learned is nucleophilic addition on this position. This carbonyl's carbon was electrophilic position because it's electron division. That was the chapter 1. Ketone aldehyde. And then we learned about the carboxylic acid, and now in the case there was another group here. And then that's the derivatives, any kind of heteroatoms, halide, anhydride, ester, thioester, kind of things. Right? In that case, the reaction attack still happened here on this position as a nucleophilic attack on electrophilic side. Now leaving group was this side. Right? That's why we learned about those order of reactivity, which molecule is more stable, more unstable, and that was the topic last week. Now, we start to focus on our attention on this position. This position is which position? Delta, Omicron, Gamma, Beta. This is alpha position, right? This is the alpha position. So now we pay attention to this alpha position's property. And we learned one thing. We learned that this form is a keto form, and then it can be arranged like this. And this is the inner form. And this inner form, now, if you look at here, now this position becomes a little funny, and then this can react to the electrophile. So far, we learned just about the electrophilic position on this guy, and this guy was always attacked by nucleophile. Now we are talking about nucleophilic property of alpha position. 지금까지는 이것만 찾아봤는데 이제는 알파 포지션에 있는 저 카본은 왜 좀 다르게 비해가 할까 하는 게 이번 주의 답입니다. If this is neutral, then this is keto and this is enol. If there is negative charge, remove hydroxide, remove proton, it's easy, right? From alcohol, that exchange of proton is very quick. Very quick. That's why water should be considered as kind of a network of exchanging proton all the time. Same thing for the alcohol. Same thing for the amine. Any kind of NH, OH, they can be easily exchanged. So that's why if it forms this keto form, it may be difficult to exchange it of this proton. But once it forms enol, then this alcohol, then this proton is easily exchangeable. And if we can remove this one, then this is NO, this is anion, enolate. Okay. Making anion of this guy may not be easy, but this one is relatively easy. Removing proton from alcohol, that's enolate. Then this reaction can happen, and then this act as the alpha carbon act as a nucleophile and attack electrophile. That's a different aspect. Okay, what's the relationship between these two guys? Keto form and enol form, and relationship of these two guys. Tautomer. Tautomer is equilibrium or resonance. Are you sure? Is it really equilibrium? 확실히 맞죠? That's equilibrium, right? That's equilibrium, and tautomerization is one kind of the isomerization. That's only proton is moved, that's why it's called tautomer. Even proton atom is moved, so that's why it's equilibrium and they are isomers, not resonance. Okay, if you think about this keto form versus the enol form, here and here, which one may be more preferred, do you think? Keto form or enol form? 그림에 벌써 답이 있네. Which is more preferred? Which is more dominant? If this is equilibrium, and it has hint here, right? Keto form is more dominant. How much? This much. Almost everything, 0.001%, 0.0000001% is enol form. That's why usually if we draw the ketone or aldehyde, we draw this way, not this way, because this is a majority. So majority of the molecule, they exist as keto form or aldehyde form. Majority of them, very small amount, they can form enol form, and this is equilibrium. Means this is back and forth all the time. But majority of them is keto form. But that speed usually is slow, but that speed could be accelerated by either acid or base. Let's define acid-base again. Acid, they try to attract the electron. Base, they try to donate the electron, but not permanently. Acid, they attach to this electron-rich part of oxygen, carbonyl oxygen, and electron-poor guys approach, and then try to attract this guy. This guy is very stable. Ketone is very stable. Now acid comes the close, then pull it out. It's a disturbed ketone. And then this electron withdrawing effect by acid that accelerates these isomerizations. Electron was pushed this way, attracted this way. That's how this rearrangement happens. And then this is pushed this way, and electrons are donated this way, and then it forms base. If the base is donating, this is electron rich, so it doesn't take base. But this position is electron relatively poor, and then base attack this position. I will give you more electron to you, more money to you, and then push this guy from this direction. And then this electron is pushed this way, and then it forms similar forms. So acid base, in both cases, it disturbs the stable ketone, and from the top and from the bottom. And it can form less stable form much quicker. That does not mean that this ratio is changing. Ratio may be same, but slightly affected. But just the speed of this, the back and forth, the speed is accelerated. Okay, that means this speed and this speed, both of them are activated, accelerated. Okay? So originally this speed is quite slow, but if you add acid or base, either case, pulling out or the giving the electron tentative temporarily, then that disturbed ketone, it accelerates the forming of inner bonds. Once it forms, then that the forming only happens on alpha, beta, gamma, delta position, only alpha positions. That effect is decreased very quickly because this effect is induced by this electron withdrawing effect of this carbonyl. Carbonyl is there, and the electron is withdrawn this way. That's why this position has electron poor. That's why it tends to give up this proton. 돈도 없고 가난한데 그냥 프로톤 하나 포기하면, 애 하나 포기하면 좀 낫지 않을까? Kind of situation. That's why the alpha position is quite unique. And alpha position of carbonyl is acidic position. Means they are easy to give up the proton or donate the protons. So that's why this inner formation only can happen on alpha positions. It's the same material we have seen so far. Carbonyl was there, and only we looked at the carbonyl. Carbon is electron deficient, it's electrophilic position. Nucleophile can attack directly on that, or if it's a conjugated system, 1,4 addition. 1,4 addition is also 1,2 addition directly, 1,4 addition a little remote, but that's also induced by carbonyl group. Now we think about right next to that position, and that position is even nucleophilic, not electrophilic. That's what we are studying. What is the relationship between these two? Sanjana? It's resonance, why? 파리 전자가 막 이동했는데 시그마 만드나 막 싱글그램에서 이중결합이 되고 막 그랬는데 빼배를 이루는 시그마 결합은 바뀌지 않았기 때문에 자 다시 표현하면 아톰은 변하지 않았기 때문에 일렉트론만 변했기 때문에 이거는 resonance 맞아. And here if you look at now this is inner form, right? And then this should be electronegative, it's an electron rich position, that's why it has extra electron. And then this electron could be partially donated through pi bond, right? When we studied about the electronegativity, oxygen is stronger than nitrogen, nitrogen is stronger than carbon. So from carbon is the lowest, and then nitrogen, oxygen, halide, chloride is getting stronger to this way. That effect is most strong through single bond, and electron withdrawing effect may be stronger here. But 5 electron donation effect is always giving from here. That electron is not given to this carbon. That electron is pushed given to this bond. Right? That's why that effect happens. It's one wave, and then that effect comes up to the next carbon. That's what we have seen. Also position, para position preference in electrophilic substitution. Right? 5 electron donation happens through bond, and that effect happens from this electron push here, and then that effect comes here. This electron donating effect ended up here, one carbon over. That's why this negative charged effect shows up alpha position, not to the carbonyl carbon. Sigma bond right next to the atom, but 5 bond effect is a 1 over. Okay? That's why this position becomes partially negative. Negative means electron rich. Electron rich means it becomes nucleophilic. Alpha position is a nucleophilic, and then that's why the carbon now it has a chance to react to the electrophile and then make new reaction here. Now all of a sudden, carbonyl group always electron poor and electrophile, but now all of a sudden, the next guy, alpha position, becomes nucleophilic and then attack to electrophile. So what product do you expect? Acetophenone, and doesn't have alpha proton here, nothing to be deprotonated. This one has some the protons on alpha position, and if you just draw in keto form like that, it's not easy to look at it. But now if you imagine it can form inner form, then this alpha position is nucleophile. And is there any electrophile here? Br2 is electrophile. Is it? And acylic acid catalyzed reaction. Br to Br should be same, but partially it could be this electron can be moved back and forth, and part time one side can be more negative than the other side, and then if any nucleophile attack here, then this take up this electron, and then this part can be electrophile. And under acidic condition, then the alpha position can attack that bromine, and it can form bromine product. Explanation is through the anode form, and then acid catalyzed reaction accelerated, and then this guy attack here, and then remove one bromide and generate. So here, acid catalyzed reaction, it can form inner form, and this inner form attack this brom, and then ended up with this reaction. So far, the conventional nucleophile we have learned is usually heteroatoms, O minus amine group, and at best we have learned Acyl metals, Acyl lithium, Grignard reagent. Those are typical nucleophiles. Now, new kinds of nucleophile we are learning alpha fragmentation. What to expect to do this reaction? Here you have ketone, let's say acetone, and if you add acid and maybe deuterium together, deuterated acid, what do you expect? If it forms in inner form, then inner form usually can be changed this way, and proton is moved. Actually, if it's in the middle of a lot of water, then we cannot guarantee that this proton is shifted here, right? There's a lot of proton source outside, and especially with the D2 there, then maybe this proton could be provided from the network. Once it forms the inner, anyway, it doesn't matter whether this proton is coming from here or not. It's exchangeable all the time, very quickly. Then the dominant solvent will change their position, right? 그지? then the position can be changed with the deuterium quickly. And this reaction is slow, but can be accelerated by acid. And this going back reaction, now we need to provide proton here again, right? If there are a lot of D2O there, then now we can expect to see this proton is exchanged with the D. Now in acidic conditions, if you have acetone and if you put it into the D2O, after long time, you will see that acetone protons are all exchanged with deuterium. Not only a single one, it can be multiple. The proton can be exchanged possibly. Right? So this is not very stable form of the molecule. It's dynamically changing, and then the mechanism is through. What if you add halide, halogen? We just have seen, right? Cl2, Br2, I2, kind of halogen, they act as electrophile. We already have seen this kind of acidic condition, and then if you add this halogen, then halogen exchange kind of this. This reaction, what's the mechanism of this reaction? Nucleophile attacked this position. This is the SN2 reactions. Okay. Attack and then push out. Okay, what to expect? Now we learned the one step, and alpha position can act as a nucleophile. That's what we have just learned. Could be accelerated by acid or base, right? And then that can attack acid there, and then Br2 there, and then you can expect the product. Now you have two options: left position and right position. Which side do you think you get the first product, the bromination? You already have seen the end product of this is a bromine attack, right? Left or right? If you think about the intermediate is an analyte, right? Analyte is intermediate. It's a double bond. Double bond is more stable when then you can get the answer. Which double bond is more stable? More substrate, is more stable, right? That's why it has a chance to form analyte this way, and this one is more substrate. So that's why we do this reaction. Bromination reaction happens all more substrate positions. If it is a 2 Acyl there, then there is no further proton, then the reaction doesn't happen. Right? But it's a single Acyl, then one position is still available, and that reaction can happen this way. Now here, one more step, if you add the base, and heat it up, expecting something, and the product is maybe elimination product, then what do you expect? Base attack what? Base attack proton. Take up the proton. And elimination reaction, I gave you the hint. Then this pyridine is a weak base, but with the heat, this base attacked the proton. And if there is a reasonable leaving group here, then this proton can be captured here. Then push. Then it can form alpha beta unsaturated ketone. Alpha beta unsaturated ketone is more stable than other positions, so it doesn't happen this way, it happens this way, and there is reasonably good leaving group there. So one step reaction was an alpha position, the carbonyl alpha position act as nucleophile, attack the brom, and then brominate it. And this is alpha position, and always the beta position is kind of the attractive position for base to generate this contributed system. Okay. What reaction do you expect? We already talked about this. Acetone in T2O and adding a small amount of water. Over the time, we would expect one deuterium exchange, and over the time, with all of those protons will be dominantly exchanged by deuterium. Right? Deuterium, proton, it's almost the same, chemically almost identical. Just the weight is double. Reaction speed is slightly slower. Otherwise, chemical property is almost the same. Okay, what reaction do you expect? Now, there are more reagents here. And in the writing, the chemical reaction, if you have one something, two something, what does that mean? So otherwise, you added this one first and then added this one separately. Okay. You wait until this reaction is finished, and then you added the second one. Then you write it this way. If you have one comma and everything together, that means you added everything together. Okay. Now you added this one first. Now two reagents. PBr3, what's the product? You add the PBr3 to acid. 뭐가 만들어질까? 성빈, 벌써. What to expect? If you add the PBr3 to acid. Acid, bromide, yes. If you add the PBr3, then this OH is exchanged. The reaction mechanism is O minus attack here, and then Br coming back, attack here, push out. And acyl halide is formed. That's one reaction. And there's a nucleophile electrophile here too. And we have an alpha position, right? If you don't have this, then the product is acyl bromide. That's it. Now, in this case, acyl bromide was formed as an intermediate, and then these guys attack this bromine, and then bromine is generated. And second step is water. Water coming in and then attack here again, and then removed. Here is the mechanism. So first step, PBr3 act and then generated this acyl bromide, reactive one. But before water is added, and then electrophile is added, and alpha position is activated and attacked, and then bromination happens. And then water added. This is very reactive position, the top one, right, among acid reagent. And then water attacked, and then it regenerate the acid. Usually this reaction we don't want, right? Acyl halide is more expensive and more reactive reagent. You don't want to destroy with water, but if you need to recover the acid, and the purpose of this reagent is to protect these positions. With acid, maybe the alpha position reaction doesn't happen smoothly. So by adding PBr3, partially protected, reactive one will protect it, and then alpha position react with the electrophile, and then hydrolysis to regenerate this acid. Okay. Then how will you make this reaction happens? 앞에도 좀 응용해 보면 starting from acid, ending with ester, and alpha position bromination is similar. How will you do it? 상황. 혜윤? PBr3, and then we can convert this into Br, and then 벌써 불러? 무슨 부르면 다시 돌아오겠네, 알콜로. 상황? BR2랑 PBr3를 먼저 넣고, 그러면 여기에 BR이 들어가고 여기도 BR이 들어가겠네. And then 메탄올을 집어넣으면 되겠네, 끝에. 그러면 아실 할라이드에서 메탄올을 집어넣었으니까 메탄올 attack that position, and then this is ended up as ester. ester, acid, amide, right? So instead of water, you add methanol at the end. Then you quench the reaction by adding this guy to acyl halide. Then you can generate methyl ester. Very good. Okay, let's think about the acidity of alkyl carbon. We said that's acidic. Now, how strongly acidic? We don't know, right? So let's check this acidity. Okay, the alpha position of acidity, if pKa wise is about 20. Now, to deprotonate this position, this alpha position, alkoxide is strong enough or not? What is the pKa of alkoxide? pKa of alcohol? 16, right? This is about 20. That basicity is not strong enough to efficiently deprotonate this alpha position. Small portion maybe, but to fully deprotonate, at least the pKa wise, it should be higher than 20. Then it can dominantly remove that proton. That's acidity issue. About 20. And as a reference, now if this is a 20, this seems like it's a quite relatively weak acid. Not so strong. It's less acidic than, it's a little stronger, less acidic than alcohol. Right? Now, in comparison, if this is a simple alkane pK is about 60. This is reference for that. Acidic than this, but still this is not the acidic enough. We need a very strong base to remove it. Alkoxide, sodium hydroxide is not enough to fully deprotonate from that position. So anyway, if there is any base and then deprotonate, and then let's think, this is ketoform. And then this alpha position is sp3. CH3 is there, right? sp3. And this is sp2. If you remove one proton out of it, and it becomes this kind of anion, and this is similar to allylic anion, isn't it? Allylic cation or allylic anion, both of them is becoming, this position becomes sp2 like the form, and all of those structure is a planar. That's why allylic position is usually more reactive than other positions. It behaves as this is kind of a conjugated system, small one, but conjugated system. That means this can be easily in resonance form can be formed. This electron can be shared. That's kind of conjugation system. Through these three bonds, these electrons are moved back and forth together. Carbocation, allylic cation is a similar situations. It's a 2 electrons moving around. In this case, 4 electrons moving around. The electron number is different, but it's a planar structure. It's behaved like in the same box. Okay. Once it is formed, like anion form, now this one is easily can form this, the anion form, like this. And utilizing this now to deprotonate that alpha position, we needed to have much stronger base, and this is a candidate. This amine, I said pKa is 36. So this is much weaker acid, so that's why it can become much stronger base. So that's why 36 is much higher number than 20. So this can be used. Did you notice anything strange here? This pKa value is reasonable. Today we learned about the review about the pKa of amine, ammonium kind of things, right? What is the pKa of amine? Pyridine was 5. Acrylamine? About 10. Why all of a sudden this amine is 36? What's wrong here? Why this is so special? Because this is very hindered or secondary amine? Why this one is so special, which has a very different pKa. 10 to 10 and the 36 is a totally different story, right? Why is it? 누가 설명 좀 해봐. 조 설명 좀 해봐. Why is it? Why? 일렉트론 위드론 이펙트 때문에 아이소프로필에 아니야. 지우고 없었어. 지우가 답해볼래? 그건 아니지. 잘 없었지. Why is it? 나한테 약간 힌트를 줬는데. We are comparing totally different reaction right now. The previous, the pKa was protonated forms removing proton. Basicity we are talking about. In this case, we are talking about this one removing this proton to make an anion form. This is a different reaction. Okay. We have this kind of amine, and one reaction can be this reaction. Here the pKa value is around about 10. Okay. Assuming that this is an acid, and then deprotonating or the proton providing power is like this. In this terms, this is a weak acid, similar to phenol. Right? That's why at pH 7, only one can donate proton out of 1,000. That's a weak base, a weak acid. It's a weak acid, that's why this is relatively strong base. Now here we are talking about this reaction. In this reaction, it's removing this proton to becomes anion. This anion, this is amine, ammonium, and this one hydrogen, proton, hydride, right? Amine, ammonium, 했잖아. This is called as amide. It's the same name with a CONH2 amide, but anion of nitrogen is also called as amide. Okay, this one now pKa value is 36. That means this is a very, very bad, weak acid. Right? This is a very weak acid. That means that this is very strong base. Okay. Now with this 36, it's a conjugated base. It's much stronger base than the pKa 20 of alpha carbonate. Then if you add this reagent, then we can deprotonate the reagents. And then among different amine group, this was chosen with an isopropyl in two positions to make it intentionally very bulky. Then we can suppress that amine, act as a nucleophile. We just want to use that reagent as a base, not as a nucleophile. And that's why it's this kind of a bulky isopropyl group. And then very hindered these two positions. And then this one, rather than it act as nucleophile, it just act as a base. Only proton can be accessed here. And the other position of bulky electrophile position may not have accessible to this. To make this reagent, what reagent do you think you can use? To remove this, then there should be even stronger base than this, right? then this reaction can happen. That option was lithium alkyl lithium reagents. Alkyl lithium reagents, it can act as a nucleophile, reasonably good nucleophile like grignard reagent. And if you use this as a base, then there is a dangerous point that possibility that act as a nucleophile, you don't want it. That's why generated this kind of strong base utilizing this. Maybe one of those strongest base in organic chemistry. And alkyl lithium reagent and deproton into this position, and then this guy becomes alkane, very simple alkane, cheap material, butan gas. Very expensive reagent becomes very cheap material, but it generates this reagent, strong base. Lithium diisopropylamide, abbreviated as LDA, strong base, pKa36. Now, if you use this reagent, then you can deprotonate the upper position. This ketone, you add LDA. If you add with the sodium hydroxide or sodium ethoxide, the protonation cannot be completed. But with this, now you can convert almost every molecule into this anolated form. Okay, because this is much stronger than this. pKa about 20, and this guy is pKa 36. And then you can do this reaction. How about you have alpha position, double alpha position? Here, this position is an alpha position to this carbonyl, and at the same time, this is alpha position of this phenol too. Then this position becomes more acidic or less acidic. Electron is withdrawing this way and also this way. If it has only one, pK was about 10, right? pK was about 20, right? Now, if it induced this way and also this way, then acidity becomes higher or lower. 수연아, 김수연. 둘 중에 하나인데. Becomes higher or lower. More acidic, less acidic. It becomes more acidic. Right? This side is electron withdrawing this way and this way. Because of this electron withdrawing effect, it becomes acidic. Now it has a 2 and more acidic. pKa, what pKa to expect? Originally it was a 20, we have a 2. How about 10? Yeah, this is about 10. If you have one position and two position, then pKa drops almost 10. Now, if this is a 10, then can you use alkoxide as a base or sodium hydroxide? Yes. Those were pK was 16, right? Now this is okay. If it has a 2 position, then simple sodium hydroxide, sodium ethoxide, they can be used as a base to fully deproton into this position. That means LDA should be much more expensive reagent and more dangerous to use. And if you have a 2 position of alpha, double alpha position, then this is much more easier to use for organic chemistry mechanism. Right? So based on this, now let's compare this pKa. pKa of alpha position, carboxylate about 4, 5. So the exact number is not important. 3, 4, 5, let's say 4 carboxylic acid. And this alpha position about 20 ketone position. Now, if you compare with the different substituents, alkyl group is electron donating, right? Hydrogen is a less electron donating. If it has a more electron withdrawing group, then this position becomes more acidic, right? Now, donating effect wise, this is electron donating effect about 20. This is not donating. That's why relatively more withdrawing effect. Aldehyde is like about 100 times more acidic. If there's any heteroatoms, you remember when you had electrophilic substitution, there was activating group and deactivating group, right? Which one was the strongest activating group? electrophilic substitution, and benzene itself is nucleophile. Then electron donating group activated the reactivity, and electron donating effect, the strongest one was amine group, and then alkoxide, right? And alkyl group has a little effect. And how was the halide? Halide has a double effect, withdrawing through sigma bond, donating through pi bond. That's why the pi effect is still also para positioning, but overall reactivity wise activated or deactivated? Deactivated and para also, right? That means the overall effect of a halide is electron withdrawing effect. Due to the electron donating effect. Right? Electron withdrawing increase acidity. Electron withdrawing with a halide increase acidity. Donating effect of oxygen is a decreasing acidity, nitrogen even more decreasing acidity. So this is the same trend of electrophilic substitution, whether these groups are electron donating or withdrawing. Acidity, electron withdrawing is more favorable because it can stabilize the anion generated by protonation, the deprotonation. Right? Removing the proton, and then leftover anion should be stabilized by electron withdrawing group. So electron withdrawing effect increase the acidity, electron donating decrease the acidity. That's for our composition. Okay. Using this, now if you think, now it's two positions. Out of this A, B, C, which one is the strongest acidic position? Out of four, let's say, two here, one here, one here. Which position is the strongest acidic position? Regina? Which one is the strongest acidic position? 이거 두 개 먼저 비교해 볼까? 이거 두 개 비교하면 이 프로톤이랑 이 프로톤이랑 누가 더 acidic한가? 탭을 보고 연습해봐. Electron withdrawing, donating, strongly donating, double donating, withdrawing, and here this one is donating. That's why this is less acidic. This is a little stronger. And comparing these two, this is a single alpha position. This is a double alpha position, and this one may be around 20 pKa. This one may be around 10 pKa. pKa 10 difference is billion times stronger. Okay. 그래서 이렇게 보면 이제 헬기가 돌아오고 조금만 더 하자. Okay, reaction of this type. Now that's why double position of alpha position is very useful reagent. And then this reagent's name is memorable. This reagent is malonic acid. And anion forming of this guy is malonate. Okay, double alpha position of this guy. Then you can deprotonate this guy with simple reagent like the sodium ethoxide or sodium hydroxide and cheap base, and then you can add the electrophile, then you can do the reaction like this. Two position. Okay. Even this reaction can happen one more time. One alkyl group is added here, and then add this again, base again, and then second electrophile, and then this reaction can happen again. Useful. You can control those reactions. One reaction or two reactions. Now, even further, after you made a single added product, and then you add water and heat, what do you expect? You have ester, you added the water and acid. Once again, what product do you expect? Ester, you added the water and acid. Excess amount of water. heating. Hydrolysis, right? You did acid and water. You may expect hydrolysis, but that's not the end. It goes further, and then lost one CO2, one group is removed. First, the product should be hydrolyzed here. COH here, COH here. And it goes further, and then one carboxyl is removed. What happens? This happens. One acid, two acid, and internally they are exchanging this electron, similar to pericyclic reaction. And then by this electron donating effect, and then one molecule, once carboxylate is removed by carbon dioxide, then end result is you have only single carboxylate and this I group is introduced. Originally, to use cheap material, they chose two carboxylate material, malonate, and then I group is introduced. And later, you may not need both of those the carboxylate, you just need only one. Then, one extra carboxylate can be removed by this simple hit. And this can happen not only those diacid, one side is ketone or aldehyde, the other side is acid. Still same thing can happen. So only this side can be removed by this rearrangement. So this can be quite useful if you have this acetyl group, then this acetyl group can be easily, acetate group easily can be removed after the reactions. Utilize it for the reactivity in the beginning. pKa20 becomes pKa10, so you can use the cheap material, not LDA. You can use sodium hydroxide, much cheaper. And then later you can remove this. Now what do you think? Here, double position, ethyl malonate, and then you use this guy and then sodium methoxide and do this reaction, then this will attack here, right? So you may form this first. And then if you heat it up, then you lose one of these and then generate the acid. You can do this reaction one more time and still one reaction site left. Again, sodium methoxide, and then to the second reaction, then you can generate two sites added. To remove one of these, what do you need to do? China? What do you need to do? To remove one carboxylate, add water and acid and heat it, then one material can be removed and then you can generate this. Quite useful reagent. Right? So if this happens intramolecularly, two reaction sites, and then this guy can attack here and here, it can form this cyclic the product. And then if you add here water and acid, what do you expect? One is removed, and then carboxylate, single carboxylate is left over here. Okay. 자, 오늘 상당히 새로운 거로 배웠는데 지금까지 했던 거는 카르보닐 포지션이 일렉트로필릭 사이트로만 작용하는 걸 배웠는데 처음으로 알파 포지션은 뉴클로필릭하게도 될 수가 있냐 하는 걸 배웠고 처음 배운 거기 때문에 이 부분은 목요일날 다시 일부 반복하고 조금 더 확장하는 거니까 오늘 배웠던 거 잘 정리해보고 생각해보고 목요일날 계속 진행하겠습니다. 자, 이번 주 이거 배우고 나면 한 주만 더 배우고 나면 비슷한 반응인데 그게 반응이 끝나고 난 다음에 컨덴세이션이 일어날 거냐 하는 거 배우고 나면 카르보닐 다 배워. 그리고 시험으로 들어요. 수업은 목요일날 할 거고 오늘 수업은 여기까지.